Welcome back to the lectures on Introduction to Quantum Chemistry and Molecular Spectroscopy. This is a very short lecture in which my only purpose is to tell you how to get the time independent Schrödinger equation from the time dependent Schrödinger equation when the Hamiltonian is time independent. You see, h of x tells you that h is only a function of the position variables that the wave function psi is also a function of. Psi is a function of both position and time. The Hamiltonian is only a function of position, that is, it is independent of time. We say such Hamiltonian systems are conservative systems, but the language apart or definitions apart, the Schrödinger equation time dependent was introduced to you in a lecture earlier as I h bar or h by 2 pi, the partial derivative of a function called the wave function of the system with respect to time, dou psi by dou of t, and that is equated to the action of the Hamiltonian. H of x is the total energy function of the system, and it is a function of the position. It is also a function of the derivatives of position because of the momentum operator and so on. The Hamiltonian is an operator function and it acts on the wave function psi of x t. Now, if the Hamiltonian is time independent, how do we get this equation h of x times a function which is only dependent on position, a capital psi of x? This is different from this, and that is equal to a constant which has the dimensions of the Hamiltonian, namely the energy, times the same capital psi function. Now, the process is to assume the existence of separability for such problems, namely to write psi of x comma t as propose. We do not know what psi of x of t is, but we propose that the variables of the function psi, the wave function x and t, can be separated in such a way that there is a function which only depends on the coordinate variable or the position variable, and there is another function which is only dependent on the time variable, and this is nothing but the product. Psi of x of t, t of t is a product. This is called separation of variables. You have to be careful about what it means. I will give you an example for what it is and what it is not. For example, if we have a function cosine k x and sine k l of t, this if psi of x, for example, is that, then this is an example of a similar function, that is the function here. The capital psi of x is the cosine k x, the capital T of t is the sine L of t. The variables are separated. Likewise, if psi of x of t is exponential I, for example, omega t, some constant omega and the time variable, and another constant k and x, if you have that. Okay. This is again its exponential I omega t times exponential I k x. So, this is the t of t and this is the psi of x. So, here is the psi of x and this is the t of t. Okay. So, that such functions exist is the assumption here for solving Hamiltonian systems which do not depend on time. On the other hand, a function such as cosine k x sine say L t plus cosine, let's write some other example, sine k x cosine L t, which is nothing other than sine of k x plus L t. Okay. Now, this is not separable. it cannot be written as a function that is only dependent on x and another function that is only dependent on t. It is a linear, it is a combination of multiple such functions. They cannot be expressed as a sin kx plus L of t cannot be expressed as sin kx plus times some other function. Therefore, this is not separable. So, this is the example of what may not be there. Okay. Another example is if you do the same thing, if you do e to the I omega t plus kx, but suppose we have this function then with a square on it, then you know this is a problem too. It is e to the I omega square t square plus k squared x square plus 2 omega k x t, and if you write this, it is e to the I omega square t square, a function of time only, a function of I k square x square, but it is also a function of e to the 2 I omega k x t, and this may not be separable into something called a function of x only and a function of t only. Okay. Therefore, there are examples for what is separable and what are separable and what are not separable. Let us assume that for our purpose that we can write the wave function in such a way that it is a product of a wave function that depends only on x, a wave function that depends only on t, and then apply the algebraic tool. Therefore, if we substitute that I h bar d by dou t of capital psi of x t of t is equal to h, the Hamiltonian operator with a hat on it, I forgot to write that earlier, h of x psi of x t of t, the Hamiltonian operator which contains coordinate functions x as well as derivatives on x will only have its action on psi of x, it will not change anything to do with t of t. Therefore, this can be written like that because the Hamiltonian does not have any derivatives or any others which is a function of t. Therefore, it is only that. That is what I said when the Hamiltonian is time independent. Now, here it is a partial derivative with respect to time, therefore, it is only going to act on the variables which on the functions which contain time as the variable. Therefore, this will also be written as I h bar dou of t by dou t and psi of x. Okay. Therefore, this is equal to h tilde of x psi of x and t of t. Okay. Now, if we divide by the product, divide by psi of x t of t, then what we get? We get 1 by t of t, the psi of x is gone. What we have is I h bar dt by dt, because the partial derivative on a function with respect to time and the function is only time dependent, then it is a total derivative. This is equal to 1 by capital psi of x h of x psi of x. Please understand that you cannot cancel the psi with this psi because the Hamiltonian contains derivatives and therefore, it has momentum operator p square, p momentum squared operator. Therefore, the p operator is a derivative in the coordinates, position coordinates. The derivatives may change the function to something else. Therefore, you can't cancel this psi with that. So, what is left over here, of course, what you have done is very clearly you have cancelled the psi of x with psi of x because this derivative does not affect the wave function. This does not affect the time, therefore, you have cancelled the time. So, this is what you have. Now, please remember left hand side depends only on time. And the right hand side depends only on the position coordinate or the coordinate x, only on x. Therefore, if we go back and write this, 1 by psi of x h of x psi of x is equal to 1 by t of t I h bar dt by dt only on x, only on t. They both have to be equal to something which is independent of both x and t, and therefore constant with respect to x and t, and that constant may be written by a symbol E. Now, what is the dimension of this constant? Please remember, whatever is the dimension of the wave function is cancelled by the dimension of this wave function. So, here it is a dimension of energy. H bar is energy into time divided by 2 pi, and the derivative d by dt is 1 by time, and the dimension of t is cancelled by this t of t. Therefore, both sides you have energy as the dimensioned quantity, and therefore E has to be energy dimension. Okay. Now, it is easy to solve this, and the fact that they have to be independent of each other is because of the fact that this does not depend on t, and therefore this cannot depend on t. This does not depend on x, therefore whatever is on that side, this cannot also be dependent on x. Therefore, E is to be independent of both x and t. Now, the solution is therefore h of x psi of x is equal to E times psi of x when you multiply, and also I h bar dt by dt is equal to E t of t. See, this is a partial derivative here with respect to x, and this is the partial derivative with respect to time, which is a total derivative here. This is the time independent Schrodinger equation. And the wave function psi of x of t is of course the product psi of x times t of t. Therefore, the wave function for the time independent Schrodinger equation is of course time independent itself, but the wave function for the time dependent Schrodinger equation, the wave function for the time dependent Schrodinger equation is a function of both x and t, even when the Hamiltonian is not a function of time. So, this is therefore important immediate step in the models that we want to solve. All the models that we will solve will not have time dependent Hamiltonians. We do have a part of the course containing spectroscopy, but we are not going to look at anything called the time dependent spectroscopic Hamiltonian and its solution, but we are only going to look at the molecular energy levels in spectroscopy. Therefore, there also we will not use the time dependent Schrodinger equation. Therefore, this step of changing the time dependent Schrodinger equation to a simple time independent Schrodinger equation for solving problems related to this course is something that you have to keep in mind. There will be some examples of this in your assignments or in tutorials, and in the next lecture, from the next lecture onwards, we will start looking at the model problems for the quantum mechanics, starting with the particle in a one-dimensional box, a free particle in a one-dimensional box, and with infinite potential barriers. Until then, thank you very much.